Today we're going to go over what space complexity is. We're going to be going over all this space complexity with some examples. And for space complexity video, I'm not going to actually code anything because a lot of the code that we're going to use is actually going to be our code that we used in time complexity. I'm using pretty much the same code because I just want to illustrate how space complexity and time complexity compares. So if you're not too familiar with space complexity or actually time complexity, I suggest you look at that first. So what is space complexity? Space complexity is the amount of memory used by the algorithm or the code that we write with respect to the input size to execute the code. So it's the amount of memory used by the code compared to the input size. If our input size is a certain number or certain size, how much memory does our code use? And there are three things that you want to consider. Memory may be used for three things. First one is the data space. So things like our variables or just temporary values. And second one is a program instruction. So amount of memory used to compile versions of our instruction. And third one is the execution, so function calls. But when we say space complexity, we want to consider the first one, data space. While all three are contributing factors, spell factors wrong, to space complexity, we consider data space as primary consideration, primarily focused on data space. So if you remember from time complexity, we use the same notation, O of 1 being constant and O of n being linear, right? O of 1 space complexities are things like the primitives, numbers. O of n is strings, arrays, and objects. And they all have a specific length, right? Now, there is actually one really important thing that you have to keep in mind. And did you ever hear about something called auxiliary space? And this thing is confused many times or a lot of times with space complexity. So to simply put, space complexity is a combination of auxiliary space plus the input size or the input space. And if you don't know what auxiliary means, it actually just means extra. So it's extra space. Auxiliary space is extra space or temporary space used by the algorithm or the code during the execution. So don't confuse auxiliary with space complexity. And space complexity is actually auxiliary space plus input space. But another thing that you have to keep in mind, and this is the most important thing, when we say space complexity, we often mean only the auxiliary space. So basically, space is equal to aux when we talk about space complexity. And why is that? Why don't we consider input space? Well, the reason is because we can't change our input space. Input space is pretty much given. So because we cannot improve the space we use for the input itself. So just as an arbitrary example, let's say that your teacher wants to sort something and we have an array of 5, 1, 3, 4, 2. And your teacher wants to write a code that sorts this array. And you're doing your test and you just change your input space to 1, 2, 3, 4, and 5 and just return this array. I mean, this is absurd, right? I mean, if you did this on your test, you're like changing the problem. So your teacher would be like, what are you doing, you know? So we can't change our input. So that's why we only consider auxiliary space when we talk about space complexity. If you guys find this helpful, make sure you guys like and subscribe. Thanks. Now let's go over our first space complexity, which is constant and it has a big O of O1. And this one obviously uses least amount of memory. So I'll just write lowest memory usage. We have a function named constant, and this is our function. We're looping through our array, which is given here. This is our input. And we're just simply looking for the max number or the highest number. And I just declared a max variable and just set it to negative infinity so that we can just iterate through our array and find the max. Now, what do you think is the space complexity of this function is? Well, I know that this runs at O of n. I know that this is a O of one operation, so runs. So that's the runtime. That's the time complexity. But does these matter when we compute space? Well, it actually doesn't, because we're only concerned about the space that this function takes. And if you remember, we are only concerned about the data space, right? Data space that we use. And how much or how many data space do we use? We actually use one, right? Where we declare a variable named max and set it equal to negative infinity. But as we loop through our function, we obviously change our max number each time, right? But what you have to know is that we replace it every time. So first is negative infinity, then it's gonna be 1, it's gonna be 2, 3, 4, and 5 finally. So at first iteration, we replace it with 1, next 2, 3, 4, and 5. So we are just simply replacing this max variable with the highest number, which is going to be 5 later. So this actually takes only O of 1 space, because again, we're not making an array of numbers. We're just simply replacing our current max value, and in our function, we only have a variable, only one variable, and that's max. And that's why we have a big O of 1. Now let's go over another example for constant, and we're gonna use a function named bubble, and this is actually a bubble sort if you're familiar with sorting algorithm. What we're doing is, like I said, we're just sorting an array with numbers from least to greatest, and this is our result here. Now this is our function, and how many variables do we have? We have temporary, so this is gonna be O1 because it's just a number. Is that it? Well, we actually have 2 more variables. It's I and j. So we have total of 3, O1 plus O of 1 plus O of 1. And that's what? O of 3. But you might be thinking, we have an array over here. Shouldn't this be O of n? And we're returning a new array with sorted items. So it has to be O of n, right? Well, that's actually not the case, because what we're doing for this function is we're using something called the in-place method, where we just change the elements in our original array. So we're not using a auxiliary space, aux space, and if you remember, that's extra space, right? We're not making a variable named, I don't know, let array equals an empty array and pushing in the numbers here. If that was the case, you're right, it should be O of n, but in our case, we're just changing the original array using in-place method, so that's why it's not O of n. So we have 3 variables, I, j, and temporary. So that's gonna be O of 3. But if you remember from time complexity video, we want to always simplify our big O. So what do we get in the end? We get O of 1 as our result. Now let's go over our second space complexity, which is logarithmic, and it has a big O of O log n, and this is our function. And if you remember from our time complexity video, this is exactly the same function. So each time we're looping through, we're having the number of operations. That's what it means to have a logarithmic space complexity or time complexity. We're having the number of executions. But in our case, we want to have the number of space each time, right? So we have our variable let result, and this is equal to an empty array. And each time we loop through, we're multiplying the current number by 2. And our input is array with 16 numbers, and I just did math.random multiply by 10 and then just rounded it up. So we have 16 elements, right? And if you were to have this each time you were looping through, what would the values be? And how many times are we able to have it? So first time is gonna be 8, second time is gonna be 4, third 2, and next one is 1. So how many times were we able to have our input of 16? It's 4 times, right? So this is the number of inputs that we expect in our array. And as you can see from our result over here, we got an array with 4 elements. So our result variable should have a space complexity of O log n. We're not concerned about our for loop. We're not concerned about return statement, because this has nothing to do with space complexity. But what if I had another variable here and I for loop and I just made a let current value CV is equal to array at index I. So that means I'm gonna have a O of one space because each time this iterates through, I'm saving current value, which is gonna be equal to array at index I, plus I have an array, which is going to be O log n. And remember, we want to keep only the dominant term, which is gonna be O of log n. So we keep O log n, and that's gonna be our space complexity. If our input had a size of 8, what would we expect our result to be? How many elements would it have? So it would be 4, 2, and 1. We were able to have it 3 times, so it should have a length of 3. But regardless, it's still a big O of log n for our space, so we end up with O log n. Now let's go over our linear complexity, which has a big O of n. It's O of n because the result variable will be the same size as the input, so it's kind of similar to our time complexity. It's gonna run n number of times. Well, this one is going to have n number of results or space. So we have our function here, our first one, and if you look at our input, we have a size of 5. And what we're doing is we're just iterating through, multiplying the current number by 2, and then just incrementing the counter variable, and then just we're returning our result, which we have here. So we declare 2 variables. First one is counter, next one is result. And if you remember, numbers have a space complexity of O of 1, and array, strings, and objects has a space complexity of O of n, right? And we're iterating through our array 5 times and then pushing in a number. So this is gonna have a length of 5, which is same as our input array. So this is going to have O1. So if we were to simplify our space complexity, it would be O1 plus O of n. And remember, we can get rid of our non-dominant term, so we end up with O of n for this one. Now let's go for another example for linear, and I think this one is a little harder to understand if you don't know it well. So we have our factorialized function that we use for our time complexity video, and we want to find out how much space this factorialized function take. So what do you think it's gonna be? Well, so when we talk about space, there are actually 2 things. We have an explicit space, which is what we have here, counter and result. We explicitly stated counter variable and result variable and set it equal to something. So these 2 are explicit. And there are things called implicit, where we have recursive calls here. And how many times do we have to run this? Well, let's figure it out. So our n is 4. We have to run fact 4, and then it's gonna call fact 3. Next is going to be fact 2, and then finally fact 1, because we hit our recursive case and we just exit out of all these calls. So as you can see, this takes how much space? It takes 4 recursive calls, and these are called, again, implicit space, because it's taking a space within our call. So when we have a factorial of 4, factorial of 4 is running factorial of 3, factorial of 3 is running factorial of 2, factorial of 2 is running factorial of 1. So we are making 4 spaces. So think of the bigger square as 4, smaller is 3, next one is 2, and the last one is 1. And when we hit our base case, we exit out of this one, we exit out of this one, exit out of this one, and finally we exit out of this one and return our result, which is 24. So we are making O of n because we are making n number of calls, and that's why we have O of n as our space complexity. Now let's go over linearithmic space complexity, and this one has big O of n log n, where we multiply O of n times O of log n, and that's how we get O and log n. So this is our function. We declare 2 variables, and we know that this one is O1 space complexity because this is a number. And let's find out what our result is going to be. Well, we know that we have a nested for loop, obviously, and the outer loop runs how many times? It runs array.length times. And we have our array here. I just have an array with 8 elements that's filled with a random number. So the outer loop is going to run O of n times, where n is the size of the input, so it's gonna run 8 times. And in our inner loop, it's a logarithmic loop, right? Because we are having the number of operations. So if it was 8, well, our input size is 8. How many times can we have this array? So we can do it once, twice, and 3 times. So this is going to run 3 times. And inside that loop, we're just incrementing our counter, and then we're just pushing in that number after we add 1 to the result array. So how many times are we doing this operation for? How many times does this whole thing run? Well, we know that our outer loop runs 8 times, and then our inner loop runs 3 times. So that's going to be equal to 24, right? That means that we're going to have 24 elements in our array. So length is going to be 24. But how do we figure out the big O for space complexity? Well, it's actually a multiplication of our O of n times O log n. And if you think about it, this is kind of similar to what we had for time complexity for linearithmic. Well, we are pushing in a number 24 times, which is O of n times O of log n, to our result variable. So we have O and log and time complexity, because this O of 1, we can get rid of it because this is a non-dominant term. Okay. But what if we didn't have this result.push array at index I plus 1? What if we didn't have this? Well, what do you think the big O is going to be? Well, we have counter variable, which is O of 1, and we have another variable, which is result, and that's going to be O of 1, because this array is always going to be empty. So we have O of 2, and then we simplify to O of 1. So the size of the result variable or result array matters, and we're doing this 24 times, which is O of n times O log n. And that's why we're getting the linearithmic for this one. Now let's go over our quadratic space complexity, which has an O of n squared. So we have our function, we have our nested loop, and our input size is 1, 2, 3, 4, 5. So we have 5 elements. And well, the definition of quadratic is input square, right? So we're gonna expect 25 elements. So what we're doing is we declare the variable. This is the number, so it's gonna be O of 1. Result is we'll find out. And for each loop, we're iterating through O of n times for our outer loop and O of n for our inner loop. And inside that loop, increasing our counter variable by 1 each time. And we're just adding I and j and just pushing it to our result array. Well, we know that our nested loop starts at index 0, index j is equal to 0. So that means for every number, we're doing this 5 times, we're doing this 5 times, we're doing this 5 times, 5, and 5. So how much is that total? That's total of 25 operations. And we're pushing in or increasing our space each time. So our space complexity will be O of 1 plus O of 1 plus O of 1. And then we have our O of n times O of n. We can get rid of our non-dominant terms. I'm just going to get rid of this, and we're left with O of n squared. So quadratic is relatively more straightforward. It's our typical nested for loop. Now let's go over our exponential space complexity. So we have our similar looking function, and we declared few variables. So length, I destructured length from array. So this is going to give me the length of the array, which is going to be 5. But this is still O of 1 because it's just a number. And counter is just going to be a number. And this I is going to be just a number. And let's figure out what our result is going to be. So when our input is 5, what is our space going to be? Well, how big is our result variable going to be? So we're looping through, we're doing it until I is less than math power to 2 length. So that's 2 to the length, which is 5. And this is the same thing as 2 times 2 times 2 times 2 times 2, which is 32. So we're doing this pretty much 32 times, and we increment by 1 each time. We're increasing our counter variable, and we're just pushing in the number I. And later, we're just returning how many times this function ran. So I think this is more straightforward. what is our space complexity gonna be? Well, when our input was 5, what became our output? Our output became 32. And if you look at our for loop, we had the math power 2 to the power of 5th. And this is an exponential. And if you want, you can do other numbers here. It can be 3. It's really up to you. But right now, we're just going to be working with base of 2. So we have O of 1 for length, O of 1 for counter because it's just a number. And next one is going to be O of 2 to the n. And this is our exponential because this runs 2 to the 5th number of times, which is 32. And we're pushing in the number I 32 times. So we're going to get rid of our non-dominant terms and we're left with O of 2 to the n. Let's go over our last space complexity, which is factorial. And if you don't know what factorial is, we have our bagel notation here. So we have n with the exclamation mark, right? Where n represents the input size. So factorial of 4 exclamation, so this is the factorial size, is going to be 4 times 3 times 2 times 1. And if we had something like 3 factorial, it would be 3 times 2 times 1. So sum or product of all positive integers until 1. And if you watch the whole video, we actually went over this factorialized function before, right? So quick quiz, what is the space complexity for factorialized function? Well, it's O of n, right? Because for each call to factorialize, we're running it one more time. So if it was fact 4, it's gonna call one more time, n minus 1, which is going to be fact 3, and then fact 2, and then fact 1. So 4 times, that's O of n. And when we go to fact 1, it's gonna hit our base case, and then it's just gonna return out of all the recursive calls. Now, another question, is this implicit or explicit space? Well, if you don't remember, it's actually implicit. It's not explicitly stated. So explicit space will be something like let counter equal 0, let result equal to an empty array. We explicitly stated these two variables, whereas we did not for our factorialized function. It implicitly runs 4 number of times, and it takes 4 recursive calls, which takes in extra space. So if you were to demonstrate it using a diagram, think of the biggest box as factorial 4, and then within that call, we're running factorial 3, factorial 2, and then factorial 1. And when we hit our base case for fact 1, it's going to exit out of the most inner recursive call, and then exit out of this one, exit out of this one, exit out of this one, and then return the number 24. Okay, now let's look at our function. So this factorial that we declare is going to have a space of O of n. And we know the counter variable is the number, so it's going to be O of 1. And let's find out what kind of operations we do for our result variable. So our for loop is going to run 24 times, because 4 factorial is 24. And then we're incrementing counter by 1. And then we're pushing in a number each time this for loop runs. So that means that length of our result variable is going to be 24, which is 4 factorial. So we're going to have O of n factorial for this one. And then our I is, of course, O of 1. So what do we have? We have O of 1 plus O of 1 plus O of n for our factorial. And then it's going to be O of n factorial for our result variable. So we simplify, we get rid of our non-dominant terms. So we get rid of this. And then we can actually get rid of this one too, because compared to O of n factorial, this is nothing. So we are left with O of n. So quick question, what if we didn't have this line, result dot push index I? What would be our space complexity? Well, first of all, what would be our time complexity? Just a quiz. Well, our time complexity still will be O of n factorial, because this for loop runs O of n factorial times. But what would be our space? Well, our factorial, this one is still going to run O of n times to get the factorialized number of 24. Our counter variable is going to be still O of 1. What's our result array going to be? Well, this one is actually going to be O of 1, because no matter how many times we run this function, our result variable never increases, therefore never increasing the size of the space or space that we need. So it's going to be O of 1 plus O of 1 for I, and then plus O of n, and another O of 1 for that empty array result. So we get rid of our non-dominant terms, and then we are left with O of n. So as you can see, even though our time complexity was O of n factorial, that did not mean that our space complexity was O of n when we got rid of just this one line. So always be mindful of what kind of operations that you are doing so that you don't make any mistakes.